All right, folks, let's jump into trusses here. This is something we talked about in statics, but can certainly expand on substantially here in this class. Trusses are the most efficient structural element, mainly because they're so deep or tall that the effective moment of inertia is very, very large. So that's why they're used. It really is the least material for the span, or provides for the least material for a given span. So we'll talk about different types of trusses. There's pretty much as many types as there are imaginations. One of the cool things about the bowstring is for a simple span, uniform line load, the bowstring is the shape of the moment diagram. Kind of cool. All right. Other types, this three-hinge arch is used often for very large open span type structures. There's a cool example of this out in Wendover at the airport where the um, bombers trained out of at one point in World War I. That's actually open to the public by appointment, I believe. All right, so let's talk about the components of a truss. The first thing I want you to understand is trusses are three-dimensional elements. Even in a building truss like this, that we usually think of a planar type element, if there's not something keeping it from tipping over, we really have no truss. So in this case, the roof is what stabilizes the top of this truss and keeps it from rolling over. In a rail bridge, something like this is our top cord of the truss, bottom cord, diagonals. This little lattice structure with the two columns here, that actually is a portal frame or a moment frame. So a train can drive through here, but this frame is stiff enough that it keeps the truss from tipping over. And it receives load from those little thin bars or rods and those little lattice truss members. So looking at this, let's say this plane of the truss tried to tip over this way. It would be resisted by these diagonals in this member, which would then transmit those forces to this portal frame, and that's what keeps everything from tipping over. Kind of cool stuff. All right, planar stability of the truss. So if we're looking at just one surface of this truss, when we have triangles, we're stable. When we have not triangles, we're not stable. So a way to quickly look at a truss and decide if it's configured properly is to look for triangles. If in every panel there's a triangle like this, then we know we're okay. If there's not, we need to make a change. Okay, so I want you to take a look at these, decide if these trusses are stable or not. The next thing we need to do is find the internal forces to our truss so we can decide, or we can size the members. So if I have a truss like this and a force coming from the left, as that force enters the system, I want to know what are these forces, or compression or tension, and what are the magnitudes? Is it 500 pounds or 50,000 pounds, or possibly more? So the first thing is to start to visualize how the force moves through the truss. If this truss enters here and these are all pinned connected, this member has to push back against that member so it goes into compression. And then that member puts a force to this node, and that has to be resisted. Well, the way that happens is this member pulls this way, putting it in tension. The other thing that happens is because this force is eccentric to the connection to the earth, this truss wants to rotate clockwise. So in order to resist that, there has to be an upward force here at this reaction and a downward force here at that reaction. So let's see if I can quickly just draw in something like that. So You can see that the little dot here would be the arrowhead. Um, anyway, what happens is that puts this in compression, that into tension, and this member doesn't have any force because there's no horizontal reaction here. Okay, next if we look at this, the force is applied on the other side. These two members are zero force members, but then this horizontal force gets resisted by a compression pushing back against it this way, and then the rotation is resisted by a downward tension um, at the reaction point. All right, hopefully that helps you get kind of a feel for things. Another thing we need to take into consideration is if our truss has loads along the length between the panel points. So at the nodes here or panel points, normally in a truss we assume the load gets applied right at those intersections. But let's say you have a roof with snow on it, that member will actually also have bending like a beam in it. Turns out that can make your member size 2 to 3 times larger just to carry that bending stress. So looking at different types of analysis methods, we're going to talk today about method of joints, where we basically take one node at a time and apply the equations of equilibrium to it. Another method that's very effective is the method of sections, where we take a chunk of the truss at a location we are interested in and solve the equations of equilibrium. There's 2 equations here, 3 equations here. Then there's an old school graphical method that's just stinking rad, even though we don't really use it anymore. And really what's replaced all of these in practice today is finite element software, where you can model a truss, put the loads in, put members, sizes, materials, and the software will analyze it for you. You can check the member for design stresses and also pull out deflections. So pretty powerful stuff. But we're going to focus today on method of joins. Okay, so the first steps are we need to draw this out in plan and elevation. So we need to know how our framing is configured. So in this case, let's say that the truss is right here, and these purlins frame onto it. And this isn't the same sketch as here, or actually it is. 1, 2, 3, yeah. Anyway, those purlins create point loads on our truss. So here's the elevation view, here's the plan view. This gives us the information for the loading, and it also gives us the configuration of our truss, which both are very necessary. I guess step 2 is deciding the truss configuration. Anyway, different types of trusses, different types of loading. It's going to be a mix of what does the building geometry need and what do we need to get the engineering to work out for us. All right, next we find the external loads. So check out the load PowerPoint. You should have your load submittal done by now and can take a framing plan like this, find a tributary area to that panel point or that node, and multiply it by your unit loads. Okay, next we're going to calc out the reactions, and that's simple statics, and maybe it doesn't feel simple, and that's okay. We can sum moments about this point to find that reaction, sum moments about that point to find this reaction, and then sum of forces in the vertical direction to check that we did that correctly. All right, next we'll label the joints with letters, numbers, your aunts and uncles' names, whatever you want to do. It doesn't matter, just have something that relates to the graphic you're working off to your calculations. Okay, the next is we're going to isolate each joint and solve for the forces. So I'll draw a free body diagram of node A here and include all the loads, and any members that I cut, I'm going to represent those members as a force along the length of the member. So at joint A, I have 2 unknowns. I know my reaction, and I know this load here. With that information, I can do sum of forces horizontally, sum of forces vertically, and get the member forces. Then I can jump over to point B, do the same thing. In this case, it looks like I have 3 unknowns, but in reality, I know FAB from joint A. So what really becomes valuable is to start at a node with only 2 unknowns. If I start at a node with 3 unknowns, I simply can't solve this. All right, then I just work my way along the truss until I get to the end. I've given you some examples here, and then I've also given you this chapter that has an exhaustive example, basically the one I was just showing you, of step by step how one solves this. And as you can see, it takes some time. Each node, we set up the free body. It can be kind of tedious. And honestly, that's why other methods of analysis exist. But this is a good place to start. And at the end of the day, what we can do is have a force in each member, whether it's compression or tension. You'll notice these bottom members are in tension, the top are in compression. There's a corollary to that in just beam bending, that bending stresses for a simple span are compression at the top and tension at the bottom. All right, so use this example. There are examples, 2 examples in the PowerPoint, and briefly, this is your assignment. You'll analyze this truss, finding the members at each node, or the forces at each, the forces at each member. And same with this, you'll find the forces at each member. Okay, so I will see you in class and we can talk more about this. Please come with questions, and you will also have time to get going on this assignment in class. All right, I'll talk to you later.